section I7, impulse. Now, if we go back to basics here, we know that the force is equal to the change in momentum with respect to time, Newton's second law. And in a case where we have one dimension, a linear situation, we can write this as dp dt, the derivative, a one-dimensional problem here. And then we can write this as some average is delta p over delta t. The concept of average, like with velocity, your velocity is, say, dx dt, your instantaneous velocity. But if I'm driving in a car and say I go a distance delta x over delta t, I get some average. When I would take my children to a piano lesson in Winston-Salem from Asheville, we would go about 240 kilometers, about 150 miles. And it would take us about 3 hours, like we would stop somewhere. So that gets you 80 kilometers per hour on average. 50 miles an hour on average. Now, you're not driving that speed. Sometimes you're driving at zero. You're not driving at all. You're stopping, for example, for a rest stop. So that gives the average velocity. So this is the average force, same kind of concept. Now, the impulse is defined as the change in momentum. So it's equal to the average force times delta t. This is what the impulse is. And they'll assign that, by definition, the letter J. So that's the impulse. And I'm going to show you now that in analyzing collisions, this concept is useful. It's useful because when you have a collision, I hope this doesn't happen to you, or you have a collision, what data can you get more easily? Well, you can get the data of the velocity. If there was radar, you would know the velocity of the car, or if the person, is honest and tells us how fast they were going, they happen to look at the speedometer, that's a way. Or someone could be watching and estimate the velocity of the car, or looking at other cars in that area, how fast they were going relative to the speed limit. So in other words, the velocity of the car is something that you can figure out. Also, here, the distance traveled during the collision can be estimated by, or measured by, how much the car got pushed in. So if the car was like that or something, then it got pushed in this distance, then you could get the distance of the collision. So with that information, I'm going to show you how this formula can be very useful. So in our case, we're going to take the speed, we're going to take the initial speed, and we'll use our kinematic notation. This is the initial speed, this is the final speed. The final speed is going to be 0 after the collision. And the initial speed, we're going to take it to be 40 kilometers per hour. 25 miles per hour. And by the deformation of the car, we're going to take, say, that distance, deformation of the car, as 40.0 centimeters, which is 16 inches. So now we pull out a formula from the past, kinematics. 2 times acceleration times d is v squared minus v naught squared. And I'm going to emphasize that this is an average acceleration by putting a little bar over the top. Now, we like to have this velocity in meters per second. So if you have 40 kilometers per hour and you want to get rid of the kilometers, you have 1,000 meters. And then if you want to get rid of the hour, you need 3,600 seconds. So this is 40 times 10 over 36. And that's 40 times 5 over 18. You divide by 2, you get 5, here you get 18. And this is going to be 11.11 meters per second. So the final velocity is 0, and the initial velocity here, v naught, is 11.11 meters per second. And the distance, I have my distance, so when I put in for the distance 0.4 meters, since 40 centimeters is 0.4 meters, then I can solve for the acceleration. So I have the equation 2 times 0.4 is 0.8. So 0.8 times the average acceleration is going to be minus 11.11 squared. And here, the acceleration, we can write down as we multiply this out. This one up here is going to be 123.4 when you use a calculator on this thing. And then you're going to divide by 0.8. And just to check the units to see that I'm doing this right, this one's going to be meters per second, but I'm squaring that. So I'm going to have meters per second. I'm squaring that. But then I'm dividing by meters. So that's going to work, because I'm going to have then 1 meter in the numerator and second square. It's always good to kind of respect the units and just check yourself that way. And the minus sign means we're slowing down, a deceleration. So when you work this out, you're going to get minus 154.3 meters per second squared. And we're interested in g-force. Now g-force, you compare that with the gravity. So in other words, what you do is if you were to divide by 9.8 and you were then going to, let's see, meters per second squared, it would cancel, you would have that's how many G's you would have. So if you do that, you get like, that's minus 16 G. That's not good. And typically they report the G without the minus sign, just say 16 G. You get in a collision, get 16 G on the average. And here, did a little lookup on G forces in an amusement park ride, 2.5 or 3, and roller coasters, you know, can get up to like 6. And here, Apollo 16 reentry 7G, maximum G force on a Russian MiG 35 is 10G. So the 16 is not good. All right. So how can we use this concept of impulse to do some work to see how we can use an airbag in a way to show that the G-force can be reduced? So what we would like to do is find that delta T. Now that delta T is not easy to find, but see the other things that we do know, the velocity and the distance we could find, we can now get that delta T by using kinematics. X is equal to x naught plus 1/2 the average speed, or the average speed. X is x naught plus the average speed times t. And now we can enter data. Let's say this is going to be 0. We start at 0, and then we're going to move 0.4 meters. And here we're going to have, this is going to be 11.11, and this is going to be 0. And now we can solve for the t. we're going to get here, bring the 2 over the other side, we'll have the 0.8 meters on the other side. And then we're going to divide by the V0, which is 11.11. And if I put the units in, I'll have meters per second. See, the meters will cancel, the second, 1/second will flip up. And this will be 0.072 seconds, which is equal to, if I bring the decimal over 3, that's 72 milliseconds. You know, where milli stands for 1,000th. So see how we got this milliseconds out of this data that we had in the problem. So for the impulse, the average force times the delta t, this is going to be a constant for our analysis. We're going to see what an airbag can do here. So if this is maybe a constant, as we work this out, we're going to have the g-force. We know the g-force is going to be 16 g, and I'm going to put down 72 milliseconds divided by a new delta t that's going to be different because of the airbag, where this is going to be in milliseconds. So this is milliseconds. So what I'm doing is saying, okay, given the impulse of this accident, and that's basically a constant that's determined by the data of the accident, then the g-force, which I figured out with 72 milliseconds, is going to be 16 g. If I could make that delta t longer than 72, I will cut down the g-force. So this is the idea of the analysis. This is given as a constant based on the collision. And I already figured out the g-force in the collision to be 16 g. That's correlated with 72 milliseconds. So I'm setting up a ratio where if I make that delta t bigger, so that the force will be, say, for example, it was twice as long. If it was 144 milliseconds, then the force would be 1/2, the g-force would be 1/2. Everything's going to go down, see, proportionally. So this is a nice formula to play with now. The g-force, in this case, if I multiply this out, I'll have 1152 g over delta t in milliseconds. And now I can do an analysis. If the delta t is 72, what it is, I get 16 g. But suppose I make the delta t 80 milliseconds, then the g-force goes down. See, 90 goes down. Remember when it was 140, roughly double, it's going to be roughly 1/2 the g-force, see, around 8. And this is a nice little table to work with. So now we're going to look at what happens during the deployment of an airbag. At 0 milliseconds, the car begins its contact with the tree. Collision is in process. At 15 milliseconds, the sensor decides to deploy the airbag. Some realistic data here. And in 35 milliseconds, the airbag is finished inflating. And then 60 milliseconds, the driver's in contact with the airbag. And in 100 milliseconds, the driver fully comes to rest. So that means the delta t due to the airbag is now going to be 100 milliseconds instead of the 72. So if I look at the chart where it's 100 milliseconds instead of the 72, I get about here 11.5 g. Now that's better than 16. Now the time is so short, in this case, we're looking at, let's see, that's 1/10 of a second. So that's another important thing. If you experience a g-force in a split second, that's going to be to your advantage rather than experiencing it constantly for a long period of time. So you're going to experience the 10 g here is roughly 10 g. So that's roughly 10 g for about 1/10 of a second. If you're in good health and you're sitting in a way that's secure, that you should most cases be okay. So that's neat how the impulse concept becomes useful in analyzing collisions. So now we have an analogy with work. Work is force times distance, and that's the change in kinetic energy. And now impulse is force times time. Say force times time. And that's delta P, just to make an analogy here. So this is energy, kinetic energy, this is momentum. So the work is given by the integral of dx from one position to, say, position 2. And that's delta K, which is 1/2 mv final squared minus 1/2 mv initial squared. And for the impulse, I have an integral with respect to time, t1, t2, and that's equal to delta P, and that's equal to m final, v final, minus m v initial. So this is a neat analogy. So you have your work analogous to your impulse, and then x becomes a t. The change in kinetic energy becomes a change in momentum. These are your integrals for each case. Change in energy, kinetic energy, and the change in momentum. Nice analogy.